In this chapter, we will be discussing acid rain. We will talk about what it is, if it's normal, and how it's different in different areas, and how to neutralize it. Acids and bases are everywhere. Most people are familiar with acids, so we can begin our discussion there. So when you think about acids, what do we think about? Perhaps the acid rain that we hear in the news. Perhaps we think about our foods like oranges and lemons. There's one thing that all acids have in common, and that is hydrogen. There are a few different definitions for acids and bases, but we will stick to the simplest ones. Let's begin to break down acids by defining an acid. One way to define an acid is as a substance that releases hydrogen ions in aqueous solutions. Remember, an aqueous solution is one that is mainly water. A hydrogen ion is a hydrogen atom that has lost an electron. Hydrogen is the very first atom on the periodic table, so it has an atomic number of 1. This means that it has 1 proton and 1 electron. If it loses that 1 electron, all that is left is a proton. This is why hydrogen ion is sometimes simply referred to as a proton. Many people have heard of hydrochloric acid, which is right here. This is the acid in our stomachs to break down food. Notice that the chemical formula is HCl. Notice that it begins with a hydrogen atom. Remember, the one thing that most acids have in common is that they give off a hydrogen. On the right side of the equation, there's a hydrogen ion and a chlorine ion. This is because the electron from the hydrogen was given up to the chlorine. And that's what's making it an acid. H plus ions are much too reactive to exist alone. So they attach to something else, such as water molecules. When dissolved in water, each HCl donates a hydrogen ion, or a proton, to an H2O molecule, forming the H3O plus, or the hydronium ion. Often we just write H plus, but understand that it really means H3O plus. And here it is here. Notice that instead of H2O, it has a third hydrogen and it has a plus sign. So if we revisit the chemical equation on the previous slide, we see that instead of simply breaking the compound into hydrogen and chlorine, we actually react it with water in the aqueous solution. Instead of simply writing H plus on this side, we have H3O plus. As its counterpart is the base. A base is any compound that produces hydroxide ions in aqueous solutions. Characteristic properties of base is that it's bitter. It's not recommended that you actually test this, though. It's slippery when it's dissolved in water, and turns red litmus paper blue, and we're going to talk about that a little bit later. Sodium hydroxide is an example of a base. When it's added to water, the compound breaks down into its ions, just like the acid does. So on the right side of the chemical equation here, you see sodium and hydroxide is separated. Since calcium hydroxide has 2 hydroxide ions, it separates into 1 calcium and 2 hydroxides on the right. Some bases are not so cut and dry. Some do not have hydroxide in the actual equation. Ammonia is an example of this. Instead, it reacts with water first. Notice in the first equation, the ammonia and water combine to form ammonium hydroxide. Now it has that hydroxide ion to donate. In this equation, the compound breaks down to the ammonium ion and then the hydroxide ion. And that's how we get the hydroxide. When acids and bases react with each other, this is called a neutralization reaction. In neutralization reactions, hydrogen ions from the acid combine with the hydroxide ions from the base to form water. Water is neutral, and since the reaction forms water, this is why it's called the neutralization reaction. The other product is a salt, which is another word for an ionic compound. The remaining positive and negative ions from the reactions come together to form that salt. Let's take a look at another example. Hydrobromic acid with barium hydroxide. If we break both of the compounds down into its ions, we can see what's really going on. We have HBr forming H and Br, and BaOH forming Ba and OH. So the OH and the H are coming together to form the water. And then the Ba and the Br are still there floating around. The positive of one compound is coming together with the negative of the other compound. We see that then the hydrogen of the acid comes together with the hydroxide of the base to produce water. The net ionic equation that you're seeing at the bottom here is if we took the barium and bromine out of the equation, because in reality these are just floating around. They were floating around at the beginning and they're floating around at the end. So they don't really do anything. It's really the hydrogen and the OH that are doing stuff. You may have heard of a pH of an acid or a solution. This is calculated by determining the concentration of hydrogen in the solution. In any given solution, the hydrogen concentration and hydroxide concentration will always balance out. If you multiply the two together, the product will always be 1 times 10 to the negative 14. Knowing the hydroxide concentration, we can calculate the hydrogen concentration, and vice versa. This will be able to tell us the strength of the acid. To calculate the pH of a solution, you would take the log of the hydrogen concentration. If you search on your calculator, you will notice a log button. You will actually see a button on your calculator that says log. Simply type in the concentration, then press this log button. Then you will need to change the sign. So if we typed in 1.0 times 10 to the negative 3, and then hit the log button, it comes out to be negative 3. Change it to a positive 3, and voila, it's a pH of 3. Even if you have a basic solution, there's still some hydrogen in there, even if it's not very much. You would need to calculate the concentration of the hydrogen before calculating the pH. So you would divide. Once you get the hydrogen, then you can find the pH. To determine if the solution is acidic or basic, you would compare the concentrations to hydrogen and hydroxide. If they're the same, it's a neutral solution and the pH is 7. If there's more hydrogen, it's an acidic solution and the pH is going to be less than 7. If there's less hydrogen, it's a basic solution and the pH is going to be more than 7. A more common way of looking at this is to examine the pH. If the pH is between 0 and 7, it's considered an acid. If it's more than 7, it's a base. Here are the pH values of some common substances. For instance, blood here is actually slightly basic at 7.4, whereas cola is extremely acidic with 2.5. Milk of magnesia, which is used to calm an upset stomach, has a pH of 10.5, which means it's basic. This would make sense because you may want to is made to neutralize your stomach acid. Rain is naturally 5.2. Notice that there's a huge range of acid rain between 2.8 and 5.2 depending on the location. And seawater is usually pretty basic at 8.2. But notice that normal rain is actually normally acidic. That's natural. If rainwater is naturally acidic, why is the ocean water basic? 3 chemical species are responsible for maintaining the ocean pH: carbonate, bicarbonate, and carbonic acid. These 3 species work together to absorb the extra hydrogen from the acid, or giving off hydrogen when the water becomes too basic. These all come from carbon dioxide being dissolved in water. So if you look here, here's carbon dioxide. Then we have an OH and an H. That's the water. If you take away one of those hydrogens, we still have the carbon dioxide, but we have OH without the hydrogen. So this is water missing a hydrogen. And then here's the carbon dioxide again, and it's water with -2 hydrogens. So it has the ability to absorb a hydrogen there because of that, if it needs to. And that's how you get rid of the acid. Over the past 200 years, the amount of carbon dioxide in the atmosphere has increased. So more carbon dioxide is dissolved in the ocean and forming carbonic acid. The lower the ocean pH due to increased atmospheric carbon dioxide. Ocean acidification is the lowering of pH. So when we say lowering pH, that means it's becoming more acidy. Remember, acid is from 0 to 7. So if the pH is going down, it's becoming more acidy. Many species such as mollusks and coral use calcium carbonate to form their shells. How does this ocean acidification affect availability of carbonate for incorporation into their marine animal shells and skeletons? The H+ produced from the dissociation of carbonic acid reacts with the carbonate in the seawater to form bicarbonate ion. This reduces the concentration of carbonate ion in the seawater. So the calcium carbonate in the seashells of the sea creatures begins to dissolve to maintain the concentration of carbonate ions in the seawater. This is actually the most important part here, because that means that there's less carbon for those creatures. Their shells are actually getting thinner. The carbon dioxide in the atmosphere gets absorbed into the ocean waters and forms carbonic acid. Then the acid breaks up into hydrogen and bicarbonate. The hydrogen from the reaction combines with the carbonate ion that is deeper in the ocean to form bicarbonate. So notice that bicarbonate is actually formed twice. As a coral breaks down, the carbonate from the shells react with the hydrogen from the acid rain. As you can see, the ocean water neutralizes itself in both directions, from the surface and from the ocean depths. Unfortunately, the ocean is having a harder and harder time keeping up with this reaction. Scientists believe that the shells will start to thin out, and the ocean ecosystem is also diminishing. So why is rain normally acidic? Well, carbon dioxide is formed naturally in the atmosphere. This combines with the water to produce carbonic acid. This then breaks apart to hydrogen and bicarbonate ion. Remember, by definition, an acid donates a hydrogen. Rain is normally acidic. However, anything below 5 will be even more acidic than normal. You'll notice from this map that the rainwater in the east is more acidic than what is considered to be normal. This is a result of the abundance of carbon dioxide and other industrial byproducts in the air in the densely populated areas. In the west of the country, the rain is more in the normal range. The most acidic rain falls in the eastern third of the United States, with a region of lowest pH roughly the states along the Ohio Valley. The extra acidity must be originated somewhere in this heavily industrialized part of the country. Scientists measure the acidity of a solution with an experiment like a pH meter that provides a very specific value rather than a general yes-no from a litmus paper.